Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 13th, 2026, exactly 1 week ago. It introduces a Codec-aware tokenization framework that reduces the time to first token by up to 86% and cuts visual token usage by 93% compared to standard video language models. The paper is titled CoPE-VideoLM, Codec Primitives for Efficient Video Language Models. And as we'll see later, the implications for efficient video processing are really impressive. Figure 1 illustrates the core difference between traditional approaches and this new codec-aware framework. In the top red panel, existing methods treat video as dense RGB images. Decoding every frame generates a massive stack of red tokens because the model processes full images repeatedly. By contrast, the bottom blue panel shows the CoPE video language model processing raw codec data, like motion vectors, directly. This creates a sparse, efficient stream of blue tokens. The chart on the right confirms the impact, where the blue line achieves higher accuracy than the red baseline while using 80% fewer tokens. Well, Figure 2 details this codec-aware pipeline. At the bottom, the video consists of groups of pictures, starting with a full iframe followed by sparse p-frames. The iframe goes through a standard vision encoder, generating 196 tokens to serve as a detailed anchor. But the p-frames route through a lightweight delta encoder, shown in blue. This compresses the motion and residual data into just 8 tokens each. So the large language model at the top receives a hybrid stream, detailed references interleaved with tiny efficient updates, which drastically reduces the computational load. So, Figure 2 introduced the delta encoder concept. Now, Figure 3 unpacks its internal architecture. Inside the central gray block, the system splits processing into 2 specialized branches. The motion vectors in the middle row feed into an MLP and a motion transformer. Below that, the residuals, which capture pixel-level changes, pass through a standard ResNet 18 and a residual transformer. Finally, the green modules on the right are used during pre-training to align these compressed tokens with the standard vision encoder's embedding space. Alright, having seen the architecture, Table 2 puts the model to the test against general video understanding benchmarks. The listing is split between proprietary giants at the top and open source models below. In the bottom row, the proposed method, labeled Our7B, secures state-of-the-art results among its open source contenders. It achieves first place on perception test with 70.5% accuracy and leads on ACNet QA with 58.8%, confirming that the efficient codec-based tokenization maintains high performance. Well, while Table 2 showed top-line results, Table 1 now breaks down the specific trade-off between token usage and accuracy. The table compares the baseline LLAVA video model against the new approach across different sampling densities, ranging from 1 to 4 keyframes per group of pictures. Crucially, the green numbers show that incorporating sparse p-frames boosts accuracy significantly, up to 6.9% on the perception test, while the token usage remains a small fraction of the full baseline. The charts on the right confirm this efficiency, as the blue curve consistently stays above the red baseline for every token budget. Okay, while the earlier results focused on accuracy, Table 5 quantifies the actual runtime benefits. The top row shows the LLAVA Video 7B baseline, which takes nearly 2.4 seconds to generate the first token. In contrast, looking at the hours section, the most efficient setting using 1 keyframe per group of pictures slashes that time to 0.33 seconds. This represents an 86% reduction achieved by replacing heavy image processing with fast codec updates. So, Figure 4 expands on this efficiency by plotting theoretical video capacity against token limits. The x-axis tracks the token budget on a logarithmic scale, while the y-axis shows the maximum video length the model can process. The red dotted line represents a standard video language model running at 1 frame per second, which fills the context window relatively quickly. In contrast, the solid purple line represents the proposed method using just 1 keyframe per group of pictures. This configuration scales dramatically better, theoretically handling up to 8 hours of video within a 1 million token window, whereas the baseline manages less than 2 hours. Wrapping up, the key takeaway is that treating video as compressed data rather than a sequence of images unlocks massive efficiency gains. By leveraging codec primitives like motion vectors, CoPE-VideoLM processes long-form content faster without sacrificing accuracy. This could fundamentally change how AI handles real-time video understanding. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.